All right, and I don't know how I feel about this lesson. It's our final lesson on quadratics. I know you might be up as excited as I am. Oh, what else are we gonna do with our time when we're not talking about quadratics? I know. Oh, what will you do with your time? I'm not sure. I mean, Disney's bumped the Black Widow. Like, when is that ever going to come back out again? Like, what are we going to do? Oh, well, take note that this will be available for you. You can watch this video over and over again as you feel your longing, all right, for great math. Now, the good news about today is, once again, like some of the other lessons, we're really taking things that you already know and applying them. We're not going to teach you anything new as far as like skill set or mechanics, but maybe make connections between like some key phrases, some key words, and then how to use some of those things that we've talked about, like vertex, um, quadratic formula, those types of things. And there's no opener today. There's no warm up. I know it's devastating. We're just going to jump right into the work today. So now, like I said, this is going to deal with applications. And so we're going to look at some things graphically. We may look at some things through words. All right. But we'll talk about some key phrases and some key things as we go through all those different types of problems. So the graph below shows the height in feet of a small rocket t seconds after it's launched. The path of the rocket is given by the equation negative 16t squared plus 128t. So this is a graph right here of this equation. Now, so what we're going to do is we're just going to use the graph to answer some of the questions here. So how long is the rocket in the air? Well, it launches here, it goes through its path, it goes up, it hits the vertex right here, and then it comes down right here. And we know that this is ground level. So this is where h is equal to 0. So this point right here represents, all right, when it hits the ground. And so we can see that from our graph that that point, which is a solution, which is an x-intercept, all right, okay, is 8 seconds. So we see that that rocket was in the air for 8 seconds. And we want to try to use units as much as we can when we're doing application questions. Now, it says, what is the greatest height or the maximum height? Now, these are some of those key phrases that we want to make sure that we think about when we read these types of questions. So what is the greatest height of the rocket? Now, anytime we see greatest, maximum, minimum, and we're dealing with a quadratic, what we're really talking about is the vertex. All right. So remember, the x-coordinate is talking about when or where, and then the the h value or the y value is, all right, the actual maximum or minimum. So what is the greatest height that the rocket achieves? It looks like it's right about here. If we look at our scale, we have 200 to 250. I think we're going by tenths, 210, 220, 230, 240, 250. So when you look at this line right here, it looks like that maximum value is about 260 feet. All right. Now, if we wanted to be exact, all right, we could actually find the value of the vertex using the things that we've talked about. So negative b over 2a, all right, and go through that. Now, we're not going to do that now. We'll do that on some of the problems later. But right now, we're just kind of trying to build an image of what some of those things represent and some of the words, right? So how high is the rocket after 1 second? So I need to come over to my graph, and here's 1. And I need to go up, right, until I find, and it looks like it's right about here. All right, so it looks like we're somewhere between 100 and 110. So I'm just going to estimate that to be about 105. All right, and that's feet. All right, after 2 seconds, about how high is the rocket? So now, once again, we're going to come to 2 here. We're going to scroll up till we find that point. And once again, it looks like it's almost right at 200 here. So I'm just going to say it's approximately 200, all right, feet. All right, so 200 feet. All right, now, is the rocket going up or down? Well, we can look at the path here that it's definitely still on its way up, right? So it's on its way up till it hits that vertex there, and then it starts coming down. So at 2 seconds, all right, it's still going up. Now we're at 6 seconds. About how high is the rocket? So we're over here. So I'm going to go up 6. And it looks like it's about to 200 feet. So it's almost like the mirror image, all right, of what we just did here. So once again, it's about 200 feet. And is the rocket going up or down? Well, we've passed the vertex, right? So now that rocket is definitely on its way down. Okay, so now it says using the equation. So now we want to be exact, okay? So now using the equation, find the exact height of the rocket at 2 seconds. So what that means is I've got to take 2 and I'm going to plug it in for both my t's up here. So we'd have h equals negative 16, and then we're going to have 2 squared, and then plus 128 times 2. All right, and then we're going to just come right over to our calculator and just input that in. So negative 16, and then we have 2 squared, and then plus 128 times 2. And we can see what the exact height was. All right, 192. So we know it's exactly 192, maybe, feet. All right. And so you can see that the graph, it's really hard to estimate, right? And that's one of the reasons we want to use equations. We want to have more of an analytical approach than a graphical approach, is because the graph is really, it's a little hard sometimes to be exact. All right, so here's what I would like you to do. All right, you're going to answer and look at problem 2, and there's 3 parts to problem 2 here as I scroll down. Now, the first thing that it asks you to do, it says a ball is thrown in the air. The path of the ball is represented by the equation h equals negative t squared plus ht plus 8t, excuse me, with h as the height in meters and t as the time in seconds. So height in meters is your y-axis, your vertical, all right? T is time in seconds, that's going to be your x-axis or your horizontal. All right, now I want you to start by graphing the equations, all right, or graph this equation on the graph. So you're going to have to use some of those tools that we've talked about. So look at this equation, identify what form it is, all right, and start with that, and then answer questions A, B, and C. And then once again, to check your answers, either turn the video back on, all right, or have your fully worked note sheet out beside you and check your answers that way. All right, so once again, to save a little bit of time, all right, I am going to click over, all right, and look at the work here. Now, we should remember how to graph. We've done this before, all right? We have to identify what form we're in. We are in standard form, all right, which means I need to find my vertex, all right? So my A value is -1, my B value is 8, my C value is 0. So if I do our negative B over 2A, that would be -8 over 2 times -1. So -8 divided by -2 is 4. And then if I plug that back into our original equation, I get 416. So 416, all right, is the vertex for this equation, all right? And so that would be the point that I started with right here on my graph, right there, all right? Maybe, there we go, 416. Now, we also have our A value is -1. Now, on my graph, I had 2 boxes for 1 just to spread it out a little bit. Now, you didn't have to do that, so you might have 1, 2, 3, 4. That's totally fine. So your graph may look a little different from mine, but we should have some of the same values. And then vertically, I counted by 1. So 1, 2, 3, 4, 5, 6, 7, 8, because I had enough space. And since our A value is -1, I can go down 1 to the left 1, down 1 to the right 1. Now remember, 1 is 2 boxes for me. And then I can do 3A, which is what I did here. And then I can do 5A, which is what I did here. And then notice I went ahead and did 7A to take me all the way down to get those initial values. Now, once again, when we look at the key phrasing here, it says, what is the maximum height? Okay, now, anytime we see that phrase maximum, we're talking about the vertex, all right? And height is the y value. So I'm going to come over here and say, oh, well, there's the highest point right here. If I just kind of work that over there, highlight that, all right, you can see that that is 16 feet. Now, how long does it take for the ball to reach the ground? So once again, it's kicked, right, or thrown. It goes up, it hits that vertex, it's on its way down, it's on its way down, it's on its way down, and you can see it hits here at 8 seconds. Now, to use the equation, find the exact value of the height after the ball after 3 seconds, all right, we just have to take 3 and plug it in for t in both spots, which you see I did here. Throw that in our calculator, and we get that h is equal to 15. All right, so there's an example of kind of working with things both kind of graphically and analytically combined. Now let's take a look at the next problem here. All right, so once again, we have a graph here. All right, very similar to what you just did. The difference mainly being is that we have the graph already created for us, right? But we can see that we have some key phrases here. All right, so what is the maximum height? So once again, if I see the word maximum height, right? Whew, stop. Maximum height. We're talking about the vertex, so right here. Okay, that's our maximum height. All right, and then, all right, the height is the y value. So it looks like if we look at our scale, it looks like we're going up by 2. So 20, 22, 24. So I'm going to say that that's 23. All right, so we're kind of right in the middle there. So 23 feet. Okay, so now, what is the height of the diving board? Well, if the swim person jumps off the diving board, they have to have at the very, very, very beginning of the problem. And if we think about that, where is the very beginning of our graph? The very beginning of our graph is right there. All right, and so that's where they jumped off the diving board, went into the air, and then they're going to come down and hit the pool down here. All right, so now if we think about that, it looks like if we're counting by 2s, it looks like that is at 14 feet. All right, so then 14 feet. And so we call that the initial value or the initial condition depending on the type of problem. So the initial height of the swim team member, all right, on the diving team was 14 feet. Now, once again, how long until the diver reaches the water? All right, so once again, where is the water at, right? The water is when the height is 0. So that would be this point right here, all right? Now, that's an intercept question. That's a solution question. That's that type of problem. Now, it looks like it's just a little bit short of 8. So I'm going to, all right, Winter, my dog, agrees. She barked in agreement there. All right, I'm going to say 7.8 seconds. All right. Whew, stop. There we go. All right, so 7.8 seconds. Okay, so very similar to what we just did. All right, so now when we look at problem 4, so what we're going to do now is basically the same thing, but we're just going to sketch a graph to start just to give us an idea of what things look like. All right, but we're not going to really put much detail into the graph, just to give us, we just want enough of a graph to give us a visual to help us solve some of the problems here, or maybe give us an inclination to if our answers are working in the right direction. So draw a quick graph to represent the scenario. So a rocket carrying fireworks is launched from a hill 80 feet above a lake. The rocket will fall into the lake after exploding at its maximum height. So we see that key phrase there, maximum height. So that means the vertex, right? All right, the rocket's height in feet above the surface of the lake is given by this function. So h equals negative 16t squared plus 64t plus 80, where t represents seconds. So if we just draw a quick, I'm not sure why it moved back up here. So let me scroll back down here. All right, so we want to draw a quick picture of this, and it really, really wants to be at the top there for some reason. All right, so let me try this one more time. Scroll down here for me. All right, so draw a quick graph. So I'm not sure what's going on here. So let's just leave it be for now. So let's draw a quick graph. Maybe it wants to really keep going. So some things are happening here. I'm going to pause the video for a second and come back on and see if that'll speed things up. Okay, so a little movie magic here. So I paused the video and tried to sketch this graph a little bit while you guys are waiting. So if you want to pause the video and sketch that yourselves, go ahead. I apologize for the drag right now. But here we have, so it launches from a hill 80 feet above the lake. So I kind of marked that right here as 80. It goes up and explodes at its maximum height, okay? And then it falls to the lake down here, all right? So there's kind of just a sketch so what we can see, all right? So now the first question is, what is the height of the rocket after 1.5 seconds? So now we're just going to use the equation. We're going to be exact. So I just want to take 1.5 and I'm going to plug it in wherever I have a t value. So h equals, so we have negative 16, and then 1.5 squared plus 64. Man, that's just really bad. All right. So I'm not sure why it went back and did all of that. So 1.5 squared plus 64, and then times 1.5. You can see it kind of freezing up there on me. All right, and then plus 80. All right, and then we're going to just use our calculator, right? So negative 16, all right, and then 1.5 squared plus 6.4 times 1.5, and then plus 80. All right, and so we get that it's at 53.6 feet. Now what that should tell us is that it's on its way down. All right, so if we think about the problem, all right, we know it started at 80 feet and went up. All right, so if it's at 53.6, that means it's below where it started. All right, so it means it's already on its path back down after 1.5 seconds. All right, so now, let me see if it'll let me scroll more this time without having to pop all the way back up here. So now it says, how long does it take the rocket to reach its maximum height? And what is the maximum height? So once again, all right, trying to highlight some keywords for you here. All right. So maximum, maybe, here we go. Maximum height. All right, and once again, anytime we see the phrase maximum minimum, all right, what did we say that that would be, right? That is the vertex, right? So we want to find our vertex using this equation. So let me write out our values here. Maybe that's an A. All right, so A equals negative 16, and then B equals 64, and then C is 80. You can see this is very slow. All right, so I'm going to do negative B over 2A here. So X equals the opposite of B, so negative 64 divided by, maybe. All right, everything is frozen. There we go. We're free now. All right, divided by 2 times A. All right, so that equals to negative 64 divided by negative 32. All right, and that gives us 2. So, all right. All right, so maybe I did something wrong in the earlier one. That doesn't make much sense, does it? Oh, did I? Oh, that's what I did wrong. So I see my mistake. So I'll have to go back and correct this problem in just a second. So this is x equals 2. All right. And that is how long does it take to reach its maximum height, which was, nope. All right, really struggling here. All right, which was 2 seconds. So this is really slowing down, guys. And you can see it's really big and really slow. All right, and so now let me go back to this one. And I said this was on the way down, but we know the vertex is at 2. All right, and so what I did here, if you go back and look at my work, all right, somehow I hit 6.4 here. So let me go back and correct this real quick so that that problem doesn't conflict with what we just did. And let's see if that gives us a better result here. And so that should be 64, it says 6.4 times 1.5, and then plus 80. And let's see what we get this time. All right, 140. All right, so so that really changes that look. And so now it's definitely not on the way down because we know 1.5 is in front of the vertex. So based on what we just figured out here, you can see my eraser just going to town here, even though I'm done and just sitting here and waiting. All right, maybe. All right, I'm not sure what's going on here, but it really, really likes to erase. All right, so click back on our pen here, and let's adjust that to make that 140. So I apologize for that. I did not realize I had hit the wrong key there. Okay, so now what is the maximum height? So the way we find the maximum height is we have to take 2 and plug it back into our equation. So y equals, and you can see that this is taking a long time to do. So negative 16, for me to write it, you guys are probably going to be speeding past me here. 16 times 2 squared plus 64 times 2 and then plus 80. And let's see if I can put this into the calculator this time and get the right answer. So go back over here. So negative 16. All right, and then we have 2 squared plus 64 times 2. Got that 64 right that time, plus 80. All right, and 144. So we know the maximum height is 144 feet. All right, so one more together, then I'm gonna let you guys do one on your own here. All right, so now, how many seconds after it launched will the rocket hit the lake? Well, that happens right here. And the key piece to this is when it hits the lake right here, all right, what's its height? Well, the height is 0. So we have to plug 0 in to our equation. All right, so if I plug 0 into our equation here, I get 0 equals. All right, I'm gonna pause the video and write that out because I'm struggling here, and then I'll be right back on. Okay, sorry about that. Things are just really, really dragging right now with my recording software. But we plug 0 in, so we get 0 equals negative 16t squared plus 64t plus 80. And remember, this now is a solving problem. So it's equal to 0. And the tool that we're going to use is our quadratic formula, all right, because it works all the time. And a lot of times, and typically in these application questions, you're not going to get nice, pretty answers. So I wouldn't worry too much about trying to factor. So let's go right into our quadratic formula. All right, x equals, all right, the opposite of b, so negative 64. All right, and I think I'm going to, once again, I'm going to pause this and write it out, and I'll be right back on. All right, so a little movie magic there. All right, once again, so we know we've already identified a, b, and c from up here. So if I put those into the quadratic formula, I get the opposite of b, so negative 64 plus or minus b squared minus 4ac, and then all over 2 times a. So once again, if you need to pause the video to catch up with me, go ahead. All right, now what we know from our work on the quadratic formula is that we want to now simplify inside of our square root radical, right? So I'm going to take the negative 64 and bring it down, plus or minus, and I'm going to go to my calculator and do the inside of my square root here. So 64 squared minus 4 times negative, make it that negative, 16, and then times 80. All right, and then I'm going to hit enter, and that gives me 9216. So that's inside of my radical here. 9, 2, 1, 6. All right, now what we're going to do now is I'm just going to bring this up here, all right, and break it apart into our two pieces. And once again, I'm going to pause and write it out. See if you guys can write it out with me here. All right, so see if you match what I wrote here. So negative 64 plus the square root of 9216 divided by negative 32, and then x equals negative 64 minus the square root of 9216 divided by negative 32. Now we want to get our answer, so we're going to go to our calculator. All right, so negative 64, all right, plus the square root of 9216 equals, and I'm going to divide that by negative 32. And I get negative 1. Now here's the issue, right? Time, we started at time equals 0. So we got negative 1, which if we were just solving, that's a great answer, but in the context of our problem, it doesn't really make sense. So we're going to go ahead and mark that one out. We don't want that guy. So now hopefully we get a better answer with our second solution here. So negative 64 minus the square root of 9216. And hit enter, and let's divide that guy by negative 32 and see what we get. And we get positive 5. So what that tells us, if I can write it here, yeah, there we go, is that it hits the lake after 5 seconds. All right, so that was that problem. All right, so now if we look at your next problem, here's what I want you to do. Once again, final problem of the unit, all right, is I want you to work this problem on your own. Now, once again, you can pop the video back on and go through it with me to check your work, or you can use the fully worked solutions which are posted for you online. So give that a go. All right, so hopefully you've worked through this problem. All right, I'm going to skip to the work here. All right, so once again, when we see the word maximum height, that should mean, okay, I need to look for my vertex. What form am I in? And we're in standard form this time. So once again, we have to go through and do our negative b over 2a. All right, so negative 4 divided by negative 32 is 1/8. And then if you do that on your calculator, you get 0.125 seconds. So it's not in the air very long, all right, once it's been thrown, all right, to reach its maximum height. Now, notice it says, what is the maximum height? Now, this is how long it took to get there. So now we have to take this 0.125 and go back and plug it into our equation up here. And once you do that, you get that it's 382.25 feet. And so that would be the maximum height. Okay, so now what is the starting height of the rock? Well, starting means with t is equal to 0. So all we have to do for this problem is plug 0 in to our equation, all right, and we get 382 feet. So if you look here, the maximum height is not much than what it started at. So when we threw this rock, all right, we threw it very flat. We didn't really throw it up and in a kind of an arc. It was more very in a flat kind of path. All right, now C was a lot like what we did on the prior problem, but there's one additional step, right? And hopefully we can see that step here if it'll let me scroll just a little bit. I didn't want to scroll a lot. I was hoping to get the entire problem on the screen here. Little bit more. There we go. All right, so how long after the rock is thrown is it 370 feet from the ground? Well, that means that the height is 370. All right, so in the last problem, the height was 0 because that's when it hit the ground. But now we want to, okay, so where is it, okay, or how long does it take to get to 370? All right, so that means I have to put 370 in for h, which is what I did here. Very similar to what we did with 0. But here's where the additional work comes in, because in order to solve, it has to be equal to 0. So now I have to subtract that 370 from both sides. And I get 0 equals negative 16t squared plus 4t plus 18. So our a value is negative 16, our b value is 4, but our c value has changed now. It's 18. I'm going to take all those and put it into the quadratic formula like you see here. Now, once again, as we go through and we simplify, we get two solutions. We get negative 0.94, which would be working backwards in time, which really doesn't make sense. So we're going to cross that one out, and we get 1.19 seconds. All right, so after we threw it, 1.9 seconds later, it would be 370 feet from the ground. And that, my friends, wraps this unit on quadratics. And that is all for our unit on quadratics. I know. What else are you going to think about? But notice you still have homework left for this unit, all right, or for this particular lesson. So give that a go. Work through those problems. Once again, if you have questions, email us. Come to the Hangouts. Come see us. Ask your questions, all right, and then we will hopefully see each other soon. So have fun working these. Take care of yourselves. Watch a good movie. All right. See you around.